For me.
Hi, everyone. Welcome back. We're very pleased to have Richard Lechner today from Linz. And he's going to speak on restricted invertibility, subsymmetric bases, and factorization. Richard?
All right. Thanks for having me. I hope you can all see the screen now.
We do, yes.
I wish to, because of the opportunity that Keith Ball's talk gives me to tie into a little bit of restricted invertibility, and from that branch off into a factorization of the identity operator on finite dimensional and infinite dimensional spaces. So that's generally the layout of today's talk, and then we apply some of these results to subsymmetric spaces. So let's talk about restricted invertibility. And as defined in Bourgain's a priori, we start out with a normalized one unconditional basis. Oh, and by the way, right? So I'm suppressing a couple of constants here and putting them to 1 and stuff like that, just to not have too many parameters around here. Okay, so we have a one unconditional basis, and we call the span of that xn for a finite n, and the ej stars, as usual, denote the dual functionals. And we ask the following question. Given an integer n and an operator defined on the space xn, which is, well, bounded by 1, and has a delta on the diagonal, what is the largest possible subset of the integers 1 to n we can find, such that the operator restricted to the natural projection on the coordinates defined by that set is invertible and satisfies some, well, the inverse satisfies some reasonable estimate. And here's the formula for sigma. And of course, we can slightly modify that problem class by, I put it in red here, by allowing that the diagonal varies. It doesn't have to be constant equal to delta, but it has to be at least delta in absolute value. And then we adjust this by inserting this diagonal operator d to the power of -1. And here's the formula for the diagonal operator at the bottom. So we slightly modified the problem, but not really. So here is the red problem I just told you again, and we cosmetically changed a few things here. Okay, so xn again is the span of the ej. The ej are one unconditional, and now we define the space x sigma as the image of the R sigmas for each subset of the first n natural numbers. Now, given an operator n, given an operator defined on xn, which has norm 1 and well, we will call this delta large diagonal, so the diagonal is at least delta and absolute values. What is the largest subset such that this diagram commutes? That is, let's go through it. We have the small space, the restricted space, x sigma, and the identity on that space. And on the bottom, we have the operator t defined on the large space, xn. And we can factor the identity through that operator, and we can do so with some reasonable bounds. And in the language previously, that would be the specific form of those operators for the first problem class. Okay. So here's the inverse of the diagonal operator, and there you can also see the restriction operator applied. Okay. And Bugarians of theory in the paper or papers give answers to those questions. How large is it possible to, how large a set one can find? And their answer is that if the basis Ej satisfies a lower R estimate for some R in the reflexive range, and that means we have this inequality here for all scalars, Aj, then for every parameter epsilon, which can be arbitrarily close to 1, and every operator defined on Xn with norm bounded by 1 and having this constant, diagonal constant to delta, to the constant delta, there exists a subset which, in terms of cardinality, has at least n to the power of 1 minus epsilon elements, such that with this particular factorization of the identity on the small space through the operator T can be achieved. And that, of course, is a well-known and very strong theory. But as one can see, we have this restriction here on the basis that it needs to be a satisfy this lower R estimate, and that is what they exploit to get this super large lower estimate, n to the power of 1 minus epsilon. And but if one is interested in factorization, then in quantitative factorization, finite dimensional quantitative factorization, maybe one isn't that particularly concerned about the exact estimate how large one can, how large the subset is that one can choose. And then there's another answer to that problem that demands less in terms of hypotheses, but also puts out less. So define X sigma again for every subset sigma, and define the quantity tau of n for each n. And it's just taking the sum of the first n ej's and doing the same with the dual functionals ej star, and then comparing the norms and taking the minimum, or not comparing, taking the minimum of the norms. And basically, if you replay the theorem of Bugarians of theory and leave out the part that where they exploit the lower estimate, then you get the following result, and that is this observation I noted in this paper here. And that is, we have our usual operator. It has delta large diagonal, and if tau of n is, well, small enough in that sense that tau of n divided by n is less or equal than delta times some constant, then there exists a subset such that this is its lower bound. That is basically 1 over that estimate here times delta and the square root of that. And if tau of n is little o of n, then it should be clear that this gives you something, right? And here we have our factorization diagram completed with these specific operators, and well, there's a result. Let's compare them. Well, we have, as I mentioned previously, different hypotheses. Bugarians of theory have lower R estimate. In the theorem I just showed you, we have basically tau of n is little o of n. And we have different conclusions with, of course, the Bugarians of theory result being much stronger. They have n to the power of 1 minus epsilon for every epsilon, and that is what I get. And let me point out that if you have a lower R estimate, this implies the following estimate for tau of n divided by n, and it goes to 0 with n to the power of -1 of r. And plugging that estimate in gives you, and now you can see how bad it really is compared to the Bougainville result up there. They have 1 minus epsilon, and that is n to the power of 1 over 2 by r. All right, that's not so great. The thing is, the hypothesis is weaker as well. Because I showed you here, lower R estimate implies tau is little lower than. Now, if we have subsymmetric spaces, then we can do, or then Bougainville can do a little bit more. Let's first talk about what subsymmetric means. We say a normalized sequence EJ is one subsymmetric if, for one, it's unconditional, but one unconditional. And here you have what I mean by that, of course, you all know. And secondly, EJ is one spreading. That means for every increasing sequence NJ, we have that these ENJs are the same as the AJs, EJs for all scalar sequences. And by Bougainville result, again, a different paper now, they have the following. So that is now for one subsymmetric basis. Whenever T is our usual operator and you have delta on the diagonal, then there exists a subset sigma that is now, as you can see here, a constant multiple of n. And so that our factorization holds. And the only restriction they impose is some restrictions in terms of void indices. And I will not go into the details of that. You can find that in the paper I've referenced here. Okay, let's see. If one plugs in the result I mentioned with this little tau of n being little o of n, then what do we get in the case of subsymmetric basis, or one subsymmetric basis with delta large diagonal? Well, then one obtains a subset that has cardinality at least n to the power of 1 over 4, which of course is much worse than just n. So that our factorization result, such that the identity in the small space factors through T in the large space. But again, the hypothesis is weaker, so that is also something. Now, let me bridge the gap to factorization or finite dimensional quantitative factorization. The goal is slightly different. Well, let's review what restricted invertibility gives us here. Okay? So, given an operator with our usual hypothesis, we want to find, or by restricted invertibility results, we can find large subsets, whatever large means, could be linear, could be n to the power of 1 minus epsilon, or whatever. Large subsets such that we have this factorization diagram. And large means number of elements, cardinality of the set. And in case, for example, that EJ is subsymmetric, then X sigma is isomorphic to, well, any k elements are isomorphic to the space spanned by any k elements is isomorphic to the space spanned by the first k elements. Okay? That is what is written here. But one might think, hold on, what happens, say, for example, for the space LPN, and I've defined that here. HI denotes, for the remainder of this talk, the Haar function, L infinity normalized, associated to the dyadic interval I in the collection of dyadic intervals calligraphic D. And we restrict these Haar functions to the support interval being bounded from below by 2 to the power of minus n. And that span gives you the LPN. And, well, if that is the case, then the dimension of that space is 2 to the power of n plus 1. And let's see what restricted invertibility does here for us. Assume even that the cardinality of the set sigma is half of the dimension of the space. Yeah. So, and assume that this is the lowest level of dyadic intervals for the LPN space here. So that is the dyadic intervals which have measure 2 to the power of minus n. Then clearly, yeah, that is half the dimension of the space. What is that space, X sigma here, that we obtained by this hypothetical application of a restricted invertibility theorem? Well, fortunately, we can do the following here, okay? So that X sigma is isomorphic to little lp 2 to the power of n, which by discretization is again isomorphic to capital LP n minus 1, subindex n minus 1. And that is why this X sigma is of the same type of space as the Xn here. And that is true for subsymmetric spaces, and we have seen that is true for capital LP as well, although it seems didn't seem like that at the first glance, but here we are. Okay, so that is what we would obtain if that were the output of a restricted invertibility result. So we have a small space LP little n on which the identity is defined, and we factor through an operator defined on LP capital N. And we get a good estimate, in fact, by Bougain's of Rödel's result, we would get something like n plus a constant. Okay? And the reason here is reminder and warning: the dimension of the space LPN is 2 to the power of n plus 1. And that's why this is the additive here, not multiplicative. Okay? But what happens, for example, if we consider the dyadic Hardy space? And well, it's basically we take the square function and then apply the L1 norm. That is the norm on the space. And what happens there is, assume that that sigma here, the same sigma as for LPN, is the output of the restricted invertibility result. Then, well, hang on. Oh, okay. I didn't see that correctly. Then X sigma is the space L1 2 to the power of n, and that is unfortunately not H1n or H1n minus 1, whatever. So the small space up here for H1 would be different from the large space down here. And there's practically no way to get that with, or no direct way, I should say. And of course, there would be always the possibility to do some trickery, but no direct application of a restricted invertibility theorem would give you that factorization diagram. Right. even when the set is super large. It could happen that you don't get it. Can't guarantee it. Of course, you could get lucky and the set you get is nice, but there's no way in the theorem in the output of the theorem that guarantees you that. So, and that is the problem of finite dimensional quantitative factorization, and that is how we move away now from restricted invertibility. That is, for which spaces xn can we find good estimates so that the identity on the small space x little n factors through the big space x capital N, so that we have some reasonable estimates for, the large diagonal is missing. So T is large diagonal, say, for example. So that we have reasonable estimates for the factorizing operators and a good relation between capital N and little n. And using some randomization techniques, the factorization, that factorization result is true for the following spaces. That is H1n, SL infinity n, biparameter Hardy spaces H1n, HP, and HPn, H1. And the relation between capital N and little n is 100 times n. But again, I have to give this warning every time, but because it looks so much better than it actually is. 100 n translates to the following relation between the dimensions. So it's a polynomial relationship, and it's or a monomial in that case, and the order is 100. So the dimension of the big space is the dimension of the small space to the power of 100. But to be fair, previous estimates for the relation between capital N and little n in those spaces, they looked like this, okay? And it goes on and it iterates n times. So we had these iterated exponentials previously, and with some randomization techniques, you can get it down to polynomial, which is something at least. Okay, so now we've touched on restricted invertibility, moved away from that through finite dimensional quantitative factorization. Now let's get to infinite dimensional factorization. So first of all, what is that? Well, as the name suggests, we now have an infinite dimensional Banach space X and an operator defined on that space. Our goal is, generally speaking, to find conditions on the operator and on the Banach space so that there exist bounded operators E and P such that this diagram commutes. And we have reasonable estimates on E and P. If that is true, we say that the identity factors through T. Just a quick note. If I factors through T, that implies that T of X contains a subspace which is isomorphic to X and also complemented in X. Say, for example, if the Banach space X has a normalized basis EJ, then this factorization diagram is true for many Banach spaces whenever T has a large diagonal. And here's what that means. So you look at TEJ evaluated in EJ star and take the inform, and if that quantity, absolute value of that, and if that quantity is positive, we say it has large diagonal, and if that quantity is equal to delta, we say delta large diagonal. Okay, so true for many Banach spaces with if T has large diagonal. let's just note that. So if for every bounded operator T, the identity factors through T or the identity minus T, we say that X has the primary factorization property. And that shall become clear very soon why that is the name for it. And if the identity factors through every bounded operator with a large diagonal, we say that the basis, because large diagonal necessitates, well, with respect to what, and we have to say, specify the basis. If that is the case, we say the operator is a factorization property. So every bounded operator with large diagonal factorizes, is a factor of the identity, and then we say that basis has the factorization property. And a sub-goal of finding simple conditions such that this diagram is true is thereby finding simple conditions which ensure that EJ has the primary or just factorization property. And to give you a short list, and certainly incomplete list of bases that have this property, the standard unit vector basis in little LP, the Haar basis in capital LP, which is a result by Andrew, the tensor product Haar system in HPHQ, where we can also include the endpoints, that is joint work with Niels Lautzen and Paul Müller. And for one more example, it is joint work with Pavlos Motakis, Paul Müller, and Thomas Schlumprecht, shows that unconditional bases that are strategically reproducible, and strategically reproducible is a condition that is given in terms of a two-player game, and just a note, can be further generalized, but for unconditional Schauder bases, it's easier to state that result. So that's why I chose this one. And just a reminder, even in some classical Banach spaces, both properties, that is the factorization property or the primary factorization property, for example, in the mixed norm Bochner space L1 of LP, that question remained open, although there have been several pushes in that direction. Specifically, I'd like to mention Capone, who showed that LP of LQ is primary for P and Q in the reflexive range, and several more recent pushes as well. And I'm happy to announce here that very recently, and I mean really very recently, it was proved that L1 of LP has a primary factorization property and is thus primary. And that is something, and that's why I want to redirect or point out that this will be the topic of Pavlos Motakis' talk in 2 weeks here on the webinar. And the main obstacle is, if what probably many of you would have guessed, is dealing with the unconditionality of the L1 component here. And let me just quickly, just for sake of completeness, say there's more generality in that result. It's not just L1 of LP, but for some class of, or a large class of rearrangement invariant spaces as well. But okay, this is not something I will discuss any further in this talk. And again, in 2 weeks in the webinar, Pavlos Motakis will be speaking at length about this. Another obstacle that occurs in achieving these factorization results, though, is, well, if X is non-separable. Okay? And the reason for that being is that gliding hump techniques seem not to be particularly useful. And that can even be observed in nice classical spaces like little L infinity. And I wish to point out Lindenstrauss's proof that little L infinity is prime. Sorry, I have to take a step back. I forgot to tell you what primary and prime is. Let's talk about that real quick. So primary means whenever you split your space in two complemented parts, then at least one of those parts is isomorphic to the whole space. And prime means that every infinite dimensional complemented subspace is isomorphic to the whole space. Okay. So non-separability is a problem. Reason is lack of non-convergence, no gliding hump. So one has to do something different. And hidden in Lindenstrauss's proof, there is the way to do it. He uses this, it's slightly different, and I will do that, but in any case, it's in there. And let's now talk about subsymmetric Wigzar-Schauder bases. And people who know what it is can already see the non-separability coming in. Let's define a few things and then talk about the results. Okay? So, first of all, if X is an infinite dimensional Banach space with a subsymmetric basis Ej, and the bi-orthogonals are called Ej star again, then Ej star is called a subsymmetric Wigzar-Schauder basis. So, and if you scratch the word subsymmetric, then both words subsymmetric, then the sentence remains true as well. So, but we'll only talk about subsymmetric Wigzar-Schauder bases here. Okay. We say that a Wigzar-Schauder basis, or a subsymmetric Wigzar-Schauder basis, is L1 splicing, and that is a characterization by Ansorenia. If there exists a sequence of disjointly supported functionals such that we have this estimate, and that says, of course, that there exists a sequence of disjointly supported functionals xj star that are little L1 sequence. And otherwise, we say that the basis is non-L1 splicing. And that is actually what we will exploit soon. Now, let X star denote a non-separable dual Banach space, which has a subsymmetric Wigzar-Schauder basis that is also non-L1 splicing. Then every operator T on X is such that the identity, well, given an operator, the identity on X star factors through T or the identity minus T. And that gives you that the direct sum of those spaces is primary, which again is, if you split the space in two complemented subspaces, then at least one of them is isomorphic to the whole space. And examples for such spaces can be obtained by looking at certain Orlich and Lorentz sequence spaces. And here you have the Orlich function for the space X, and here you have it for the dual space. That would be an example of obtaining new spaces in which this result was previously unknown. But the following question remained unanswered in that particular paper, and that is, do non-L1 subsymmetric Wigzar-Schauder bases have the factorization property, which is, if I may remind you, if T has large diagonal, then the identity factors through T. And that question was recently answered in the affirmative. Here the question is again, and here's the answer. Yes. And let T, here's the formal statement, let T be a bounded operator on X star with delta large diagonal. Then, well, it's not the statement. No, then identity factors through T. And the main obstacle in the proof is to find block bases Bj of Ej and Dj of the dual Weierstrass-Schauler bases, so that Bj is equivalent to the Ej's and Dj is equivalent to the Ej stars, such that the Bi evaluated at Tdj is almost 0 for j less than I, and Bi evaluated at T, and that is the important thing, that's where the non-L1 splicing comes in, sum over infinitely many Aj, Dj that come after I. So I would refer to the second line here as the past, since the j's are smaller than I, and here I would refer to that as the future, since the j's are greater than the I, and the I is the present, and the present has to be large as well, in the sense of keeping the diagonal large. And to achieve these things is especially problematic that we have to do this under the following restriction, and that is the size of the support of the block bases cannot, has to be bounded, put it that way. The size of the support has to be bounded. And in fact, it is possible to do this with supports of length 2. So we can do it with just 2 elements. Since this is the only way, at least I know how to show the first condition, that is these, the block bases are in their respective, are equivalent to their respective, sorry, my tablet isn't working. Here we go. The block bases are equivalent to their respective bases in X here and X star there. And how much time exactly do I have left?
We still have, let's see, 10 minutes, 11 minutes.
Then, excuse me, let me quickly exit this presentation mode here. I'm sorry. And let's try. Okay, it's already open, great. Let's try and see how far I can get in showing you or convincing you to some degree that it is actually possible to achieve these conditions. And okay, so that works. And if one has these 4 conditions, then you're basically done. So that fits within a standard framework. And that gives you the desired factorization result. And of course, one has to make precise what is almost 0 means here, but let's not get too many confusing constants on the table. So the first thing I wish to remind you here is that Ej star is non-L1 splicing. Okay, we remember it does not contain disjointly supported L1 sequences. That is what that means. So let's start with our first lemma, and that is given x in x and eta, and well, I also need an operator on x star. And I cannot scroll. Okay, I can. And then the claim is, and also I probably need some infinite subset, just to be on the safe side here. And then the claim is there exists an infinite subset lambda of I, such that the following is, oops, following is small. And small means less than eta. And of course, now I have to define what is p lambda. Well, p lambda, I could actually define it on the Wixner-Schauder basis. Is Ej star if j is in lambda and 0 else. Okay, so the natural coordinate projection induced by the set lambda. Okay, maybe move that to the side. And let's see if we can prove this lemma. Okay. Well, assume not. So x, eta, and t are fixed. And we assume that star is true, which is not the conclusion. That means for all infinite sets lambda, we have the supremum of all x star in the unit ball of this expression is greater than eta. Oh. Well then, pick lambda j, a sequence, actually, of pairwise disjoint infinite sets. Okay. And according to star, for each infinite lambda, well, there exists an x lambda such that, well, that quantity here is greater than eta. So let's say I index them, since the lambda j's are indexed by j, the x j's are according to the lambda j's, and that's a sequence in the unit ball of X star, such that, and I actually could copy that. Let's speed things up. Okay, and here we have the J and the J. And now I say, well, let's get rid of that absolute value. Let's put an epsilon J here and pick them accordingly. And now I say, since this is true for all J, take sum, well, it's sum to some index capital N. And then I say, well, actually, exploiting the linearity here, I go in like this, and thereby, oh, and I forgot some, sorry, forgot something, that's not good. In order for that to be true, I should put some AJs here. Okay. So you, okay. I think it's clear what's happening here, right? And now we estimate and get rid of the T as well. Okay, get rid of that. And find ourselves here with a sequence, let's call that Yj, that is disjointly supported in X star, and it is L1. And that cannot happen, because we said Ej is non-L1 splicing, which is the opposite. Okay? No disjointly supported little L1. That's what non-L1 splicing says. Okay? And that's the contradiction here. And thus we have proved the lemma. And I can see I will never be able to finish the proof of the whole thing, but let me just quickly do one thing. Okay? So, oh, sorry, we construct these B's and D's inductively. End of the page, sorry, I have to be quick here. Okay. And of course, starting with something like that. Okay. And then we use the lemma we just proved such that that is as small as you want it. And there's a supremum missing. Wherever you pick X, here we have the restriction to the infinite set lambda. And if we pick the next D, D2, well, I put it that way, in P lambda X star, then B1 T D2 is small. Okay? And that is how one can achieve this diagonalization result using this well, trick that originates in Lindenstrauss's proof. That shows that L infinity is prime. And this is an abstract version of that trick, but you might be able to spot it. And so what this enables us to do is choose a large subspace, large enough that it reproduces the whole space in which we can search for our next block basis element. And I think I've stretched the time a little bit here, and I will stop now. Thank you very much.
Thank you so much, Richard. We can open for questions or comments now.
Richard, would you go back to the preceding slide? Scroll back. Yeah, and the proof. Yeah, okay, so I didn't understand that next to last line because I mean, the inequality, I mean, I see you get it for non-negative AJs. Why do you get it for every sequence AJ?
Well, let's step through it because I deleted the intermediary steps and then I forgot that I had to add the AJs and, well, okay, let's do that again slowly. So maybe I just copy it onto the next page and start a new page. All right. So that is what was written, right? And we started with X T P lambda J xj star, and all right, it's like this. Okay, that's what we started with for all J. So then I sum over all the first, I call it capital N AJs. Let's see. Okay, so that is just simply multiplying by AJ and summing. And then I say, well, actually that absolute value isn't really there. I write it like this, epsilon J. And then, actually, let me move that down there. Hope you can read that well enough. And here we have AJ.
No, I think you want to remove also the absolute value on the AJs.
Exactly. Thank you. Thank you. Exactly. That's what we do. Yes. So epsilon J is chosen so that we can remove both absolute values. So, and it's the signum. And
the epsilon J depends on both the AJs and whatever the sign is. And okay. Oh, but that's okay.
Yeah.
Your hypothesis, you're saying. No.
Yes. Sorry?
Okay, now you have the XJ star, T of XJ star. Yeah.
And yes. So, and then we, I think we're good now. Is everything more clear?
Okay, okay, so now you use the, okay, and now you use the.
Yeah, there might be a slight messing up on my part because I forgot the AJs initially. Sorry for that. Yeah. So now we're in the clear.
Okay, anybody else?
But still, you have this choice of, wait a minute, the epsilon j's that you end up with at the end then depend on the AJs, right?
No. That is just leading to a contradiction. So the yj's are epsilon j xj star. That just leads to the contradiction that shows you, hang on, shows you this lemma is true. So there is no influence going on, no epsilons or anything. It's just that lemma is true, and that's all. There's no more j's because they were just part of the construction that led to the contradiction.
Could I see the definition of non-L1 splicing again?
Yes, it's not written. I can write it real quick. It's if there is no disjointly supported L1 sequence in X star. And the disjointly supported pertains to the EJ stars.
Then I still don't see what you say.
Well, here there are two things. I wanted to show you all of that, okay? All of that. And the only thing I got to show you was this part, or part of this part here, okay? I showed you the lemma and one construction step, how to, for I equal 1, I showed you the red one, okay? So if we have that lemma, and we agree that we have proved the lemma, I hope. Do we agree on that? Is the lemma proof?
No,
No, okay.
You,
Well,
I'm just missing something.
the XJ stars are biorthogonal to an unconditional basis? Maybe you should say what are the XJ stars?
the xj stars are just norm1 vectors. I didn't, well, actually, here it is, I did. But
Oh, the whole basis is unconditional? Are you dealing with
they are disjointly supported with respect to biorthogonal functionals to an unconditional basis? Of an unconditional basis?
to a subsymmetric and therefore unconditional basis, yes.
Oh,
you see,
okay.
that's this explains. Okay.
Okay, that was the hang-up. I understand. Maybe I went over that too quickly. Okay. So that we're good then?
Yeah.
All right, great, thank you.
Yep, understood.
But I don't think XJs are the basis. XJ stars are just the functionals giving you from every disjoint set that you assumed, right? So that's the
right, but they add up unconditionally. I mean, if there are any finite
oh yeah,
number of
because
them,
the
so
basis,
this
yeah,
is,
okay.
Because
Okay. Any others? Okay. If not, thank you so much, Richard, again, for a very nice talk. So,